So we're going to have a look at solubility equilibrium. Basically what we're looking at here is a situation where we have a solid dissolved in water, but it's not really becoming aqueous. It's sitting at the bottom. So what we end up having is a solid compound moving into its ions, dissociating, and then those ions are reassociating back into the solid. We've talked about the concept of an insoluble compound, but realistically we should be using the term sparingly soluble, because a little bit of this barium sulfate, which is insoluble, sulfates are insoluble with barium, will get into solution just as this equilibrium process shows, but it's very, very small. So when we write the equilibrium expression for it, we write Kc is equal to the concentration of the products raised to their powers, which of course are 1 in this case. And there is no denominator because the barium sulfate is solid. So these equilibrium values, which we better called KSP, or the solubility product equilibrium constant, for barium sulfate is 1.1 times 10 to the negative 10, which is much, much less than 1, so it's very much laying with the reactant side. So the try this says, what is the concentration of barium and sulfate in a saturated solution of barium sulfate? So I start by writing KSP is equal to the concentration of barium and sulfate, just like we have above. And remember, it's the concentration of the products divided by the concentration of the reactant, which I don't write out because it is solid. These are aqueous, so they appear. The next thing that I'm going to do is just put in my equilibrium constant that it gave me. And because it's 1-to-1, I'm going to produce X amount of barium plus 2, and since it's the same, X amount of sulfate. You have to make sure to take into account the stoichiometry of the equation. So for example, if you had a 2 on one of the products, then that would translate to 2x, and then of course it would still be squared. So x, when I solve for this, is equal to 1.1 times 10 to the negative 10. The root, so x is equal to barium plus 2 is equal to the sulfate ion concentration, and that's equal to 1.05 times 10 to the negative 5 molar. Essentially a very, very small value compared to whatever the solid would be. So that's the basic behind what equilibrium is. So there's a connection between solubility and KSP. We have 3 terms here: solubility, molar solubility, and the solubility product constant, which is what we just finished talking about. Solubility is expressed by how many grams per liter of solute will fit into the solution. Molar solubility is the same concept but in moles per liter, and the solubility product is just the equilibrium constant. So given any one of those 3 terms, we can move back and forth just like this flow chart shows us. So let's have a really quick look at how this works. So I'm going to just zoom in here on the try this. So it says silver chromate is added to pure water at 25 degrees Celsius. Some of the salt remains undissolved at the bottom of the flask, which indicates that it is saturated. The mixture is stirred for several days to ensure that equilibrium is achieved between the undissolved silver chromate in solution. Analysis of the equilibrium solution shows that the silver ion concentration is 1.3 times 10 to the negative 4. So I know I have Ag2CrO4 in equilibrium with Ag plus 1, 2 moles of it, plus chromate. I know the concentration of silver plus is equal to 1.3 times 10 to the negative 4 molar. So if the concentration of this is 1.3 times 10 to the negative 4, because of the stoichiometry, and this is a 2 and this is a 1, the concentration of chromate must be half of that, because it's 2 to 1. So I go 1.3 times 10 to the negative 4 molar silver ion times 1 mole of the chromate for every 2 moles of the silver plus 1. And I get 6.5 times 10 to the negative 5 molar. So now I just do my KSP expression, remembering that it is the concentration of the products over the concentration of the reactants. So I have silver plus 1. Because it's a 2, I make sure to square it. Times the concentration of chromate. KSP is equal to the concentration of silver. Times the concentration of the chromate. And I end up with 1.1 times 10 to the negative 12 when I do that, which is considered the KSP for this particular reaction. So now we have calcium fluoride, a similar idea. So calcium fluoride dissociates to calcium plus 2 moles of the fluoride ion. I'm going to throw an icebox together here where the solid is not going to affect us at all. Once I put the solid in there, I have none to start with. The change is going to be plus x and plus x, leaving me with x. So this should be 2x, leaving me with 2x on the fluoride term. So KSP is equal to the concentration of Ka plus 2 plus fluoride minus squared equals 3.9 times 10 to the negative 11, which is given to us in the question. So we end up with x times 2x all squared equals 3.9 times 10 to the negative 11. Simplifying that, 4x cubed equals 3.9 times 10 to the negative 11. So x must be equal to 2.1 times 10 to the negative 4 moles per liter. So quickly, if we're solving for x, x is the concentration of calcium, but 2x is the concentration of fluoride. So because it's a 1-to-1 ratio, we want the molar solubility of calcium fluoride, then what we need to do is make sure that we figure out the calcium, because that will be the same for the calcium fluoride. So that's equal to the concentration of Ca plus 2. It asks for solubility, and it's telling you in grams per liter. But how we're going to just fix that to make sure that we get it in grams per liter, we're going to take 2.1 times 10 to the negative 4 moles per liter, which is the molar solubility, and we're going to multiply that by the molar mass of calcium fluoride. Because remember, it's for the solute, not the ion itself. So 78.1 reflects the calcium F2, the calcium fluoride. And the answer then is 1.6 times 10 to the negative 2 grams per liter. And that's how we go back and forth. So the common ion effect is the quantitative version of Le Chatelier's principle. And what Le Chatelier's principle says is that if you stress the product side, you will force the reaction to move away from that stress, basically going back towards reactants. So the common ion effect says that as you add a common ion, especially in a solubility situation, you're going to make this solution less soluble. So we're back to calcium fluoride here. And the text, I took this out of the textbook. It says the solubility of a slightly soluble salt is decreased by how the solubility of calcium fluoride decreases as NaF is added to the solution. So NaF would be the common ion, forcing the reaction to the left. So Le Chatelier predicts that adding NaF to this situation, or adding a common ion, will force the reaction to the left. So let's have a look at exactly what that would mean. So the try this says, calculate the molar solubility of calcium fluoride at 25 degrees Celsius in a solution that is A, 0.01 molar calcium nitrate, and then B is 0.01 molar sodium fluoride. So we're going to write our expression out. We have our expression all written out. Going to throw it in an ice box where the solid never matters. Now, because of the common ion, realizing that nitrates are all soluble, so this is a strong electrolyte, it's going to completely dissociate. And for every 1 mole of calcium nitrate I get, I'm going to have 1 mole of calcium ion. So my initial for calcium is 0.010 molar. My fluoride initial is 0. Stoichiometry of this tells me that I'm going to gain X and I'm going to gain 2X. So I have 0.010 plus X and 2X in the equilibrium line as I add them up. Now, when we have a solubility of 10 to the negative 11 here, and this is our initial value, if we take that initial value and divide it by 10 to the negative 11, we're going to get a number much, much greater than 500, which tells us that we really can ignore the loss of X here, which will simplify our problem a little bit. So I write KSP is equal to 3.9 times 10 to the negative 11 is equal to calcium plus 2 fluoride ion squared. So 3.9 times 10 to the negative 11 is equal to 0.01 times 2x all squared. 3.9 times 10 to the negative 11 is equal to 0.01 times 4x squared. And we find that X is equal to 3.1 times 10 to the negative 5 moles per liter. And that's the molar solubility of this compound, which is less than it would have been without any common ions. So for B, we're going to try and do the same thing, except for this time we're going to have fluoride. So as we move down, still have our ice box. Now we have none of this. So we're basically just going to have a mirrored problem where everything's just going to be exactly the same. And once again, we're going to be able to ignore any change of X here. So just to plug this along, X is going to now be equal to 3.9 times 10 to the negative 7 moles per liter. So the molar solubility of fluoride has actually gone down again. And it makes sense because it's a 2-to-1 ratio, so the effect is going to be exaggerated for the fluoride. So now we have the issue of solubility and pH. So what we're saying here is that the solubility of a compound that produces basic anion, so for example that would be like hydroxide, will become more soluble as the pH is lowered. So the example that we're giving here is magnesium hydroxide. Will produce 1 mole of magnesium and 2 moles of the hydroxide ion with a KSP of 1.8 times 10 to the negative 11. So if we just calculate the pH of that as we've done in chapter 16, we find the pH to be 10.52 with a magnesium concentration of 1.7 times 10 to the negative 4. There's no need for us to do that right now because we've done it multiple times in the last chapter. So you should be able to get that number, and it might be good practice for you to make sure that you can get those two values. So if we buffer the solution, that is, create a solution that's resistant to pH to a pH of 9, the pOH of that would then have to be whatever the difference is between 9 and 14. So 5 plus 9 is equal to 14. So pOH is equal to 9. And 10 to the negative 5 to go from pOH to the concentration of OH, is 1 times 10 to the negative 5 molar. So we write our KSP expression equal to the value up here. It's got to be the same. We plug it in and we find that the concentration of magnesium is 0.18 molar, which is quite soluble. So basically we have an increase in solubility from here to here of about 1,000 times by increasing the pH value from about 1.5. So you can extend this to a point where if you actually make this solution acidic, magnesium hydroxide will be soluble, not even sparingly soluble. So the condition here is that the basic anion has to be the conjugate base of a weak acid, not a strong one. So I have a list of them shown here. So for example, iodide is the conjugate base of hydrogen iodide, a strong acid. So iodide would not be a reasonable weak conjugate base anion. Chloride would be an example, bromine would be an example, nitrate would also be an example of that particular fact. So for this, try this, what we're going to do is we're just going to have a look at 4 compounds: nickel hydroxide, calcium carbonate, barium fluoride, and silver chloride. And for each one, we're going to write out the equilibrium expression. So nickel hydroxide solid is in equilibrium with nickel plus 2 moles of hydroxide. Calcium carbonate is in equilibrium with those 2 ions. Barium fluoride, also solid, is in equilibrium with barium plus 2 plus fluoride. And silver chloride is in equilibrium with Ag plus Cl minus. So we just want to know if this will be more soluble or not. So starting from the first one, hydroxide is a base, and it's on our list up here. So it's a basic anion. So this one will become more soluble in an acidic solution. Carbonate is the conjugate base of carbonic acid, which is a weak acid, so that's a yes. Fluoride is the conjugate base of hydrogen fluoride, which is also a weak acid. And then we get down to chloride. Well, chloride's the conjugate base of hydrochloric acid, which is a strong acid. So that's a no. And that's basically how we figure out if pH, if it's lower, will make the compound more soluble. So the last part here is precipitation reactions. And the question that we're going to be asking here is whether or not, when 2 solutions are mixed, if the concentration of the associated ions will be enough to cause a precipitation. So we know that the product of any 2 ions that are sparingly soluble cannot exceed the KSP value. So what we're going to do is we're going to check to make sure that the concentration of both of these ions, when we multiply them together, of course, and taking into account their exponents and everything like that, does not exceed this value. To do that, we're going to use the reaction quotient. The reaction quotient is used, it's the exact same expression as the KSP, but it's used when we are not sure whether or not the solution is at equilibrium. We're using it as a test to see where the current situation of the solution is with respect to the equilibrium that it will eventually reach. The question says, will a precipitate form when 10 mils of lead nitrate is added to 40 mils of sodium sulfate given a KSP for lead sulfate? So the first thing we want to do is we want to know how many moles of each of these compounds we have. So 0.010 liters of 8 times 10 to the negative 3 molar lead nitrate. Gives me 8 times 10 to the negative 5 moles of lead nitrate. And 0.040 liters times the concentration here is 5.0 times 10 to the negative 3 molar, and that's for sodium sulfate. need a calculator for this one. So when you work through that, you can actually see that the moles are given. The moles are given with respect to the volume that they were delivered in, but then after the fact, we know that we have to include the total moles, the total milliliters in this solution. So what I'm going to do is 8 times 10 to the negative 5 moles in 0.050 liters. And that's for lead sulfate. Do the same thing for the other one. So now we have sodium sulfate to figure out, 2x.4 negative. That's 4.0 times 10 to the negative 3 moles per liter. And we're interested in the sulfate here. So now I have the new concentration. So this is basically what I refer to as like a dilution effect. The final thing that we're going to do is we're going to write out our Q expression. Plus 2. And we just plug our values in now for Q. So for lead it's 1.6 times 10 to the negative 3. For sulfate it's 4.0 times 10 to the negative 3. Q is equal to 1.6 exponent 3 negative times 4 exponent 3 negative is 6.4 times 10 to the negative 6. So the last thing we have to do is just check to make sure that Q is compared to KSP. So the KSP is equal to 6.3 times 10 to the negative 7. Q is greater than KSP. So it will precipitate. And that's what we do. So basically, you find out how many moles you have of each ion. In this particular case, I have lead sulfate, so 1 mole of lead sulfate is going to produce 1 mole of lead plus 2. You got to be careful with that because, for example, had I used the nitrate up here, it's 2 moles for every 1 mole of the compound. We didn't have to use nitrate, obviously, but just something to pay attention to. And then finally, once we create our Q expression, which is our KSP, we get Q. Q is greater than KSP, so it will precipitate. If Q is equal to KSP, then we have an equilibrium. Nothing's really going to change. And then if Q is less than KSP, then we can actually continue to dissolve things.